Alright, in my previous video, we learned about thermodynamics law and then statistical thermodynamics. In these two, we assume that our thermodynamic system is nearby equilibrium, so by this condition, we can define that U as internal energy is depend on S as entropy, V as volume, and then N as number of particles. But here, this U may be depend on other variables, let's say xi index for each variables. By this dependence, we can take the differential form by using partial differentiation as this and of course by chain rule. But in reality, in experiment, we only can control some of this. For example, the pressure, for some case in volume, for some case as n number particle, and maybe the other variables as xs here. So we come to the questions. Can we use other quantity instead of U to avoid these uncontrollable variables? The answer of these questions is the goals of this video. So let's start this video by remember that here until now, we assume that system is equilibrium or at least nearby equilibriums, or for some simple case as quasi-static. But before we continue, we need to define and construct our mathematical tools to get our question answered. Here, let F be a mapping between multidimensional real number line vector space to the one-dimensional real number line or just R. F here be strictly convex function, which if you remember in my shorts video, we use inequality without equal scenarios. So by this property, we can make a graph of function, let's say like this, which we know that in strictly convex differentiable function, we have the second derivative greater than 0. Then we can pick one point at this graph of function f, which the point we pick here is about x, and the tangent line, just like this, has p as gradient or slope. Next, we need to check that all tangent line for all x as a result of mapping by f function, which here, if we remember about straight line equation, if we take the equality to the function of f, which we know this equality only happen at tangent point, so to make this equality for every possible tangent line, this constant term must be depend on p, or the gradient. And surprisingly, each tangent point for this convex function has uniquely different p. So to make this equation holds true, we need to take the optimal value of this subtraction. So we will have that each tangent point satisfy this equation that we define as f stars. And you might be thinking, what the sub here means? Here, sub or supremum means that if S is a set and U is a supremum of S, then for all x inside S, x is smaller or equals to U, or we can say as minimum upper bound. This definition has contrary with inf or infimum, which is same as supremum, but now we switch the inequality and the minimum to maximum lower bound. You might be thinking, why we define this as supremum? In this equality, assume that this f star has maximum value. So the supremum here is what we know as maximum. Because this maximum exists and this is a differentiable function, we take differential form of f star as this, which for maximum value of f star at constant p, and by looking for maximum value as df stars equals to 0, then the remaining non-zero term will be like this, which by this form, we can get this differential form. So here we get p is equals to this. So by this result, if we take these two equality true, then we can remove the supremum notation, which we know that this subtraction has tell the maximum value of f star. This equation system is what we know about Legendre transformation or just Legendre transforms. And if you notice, this transformation tells us that instead using coordinate x, we can use p as gradient of f of x with some restriction. This Legendre transform widely used in analytical mechanics, thermodynamics, and many things in physics. And if you notice that, if f is a function that tells about physical system, that f need to be a convex function for the variables that involve, which means that the system must be a stable system. In thermodynamics, we know this as equilibrium or just nearby equilibriums. Now, the mathematics tools are done constructed, and next we return to the physics system, which again we let U as first thermodynamics law internal energy, which satisfy these equations. And for reversible system, we will have this equation. And for self-calculation, we take the system as stable or at least quasi-static or very least nearby equilibriums. Next, If we use u that depend on these three variables, we will have the differential form of u as this, which mu here is chemical potential for all n particles that tell us about kind of the particle. So if in our system there is many kind of particle, we can take the differential form of u like this, which mu I is chemical potential for each I kind of particle in our system. For the stable and equilibrium, or at least nearby equilibrium system, this u is a stable function or satisfy the strictly convex function, so we can take the Legendre transform with this u. So now, let's start using Legendre transform to get our equation in the beginning little by little answered. Here in the first case, I don't want to measure the entropy because it's too out of control. So here we can define F as this equality, which later we define this as Helmholtz free energy, and by take the differential form of F, we will get the final result as this, which means that this Helmholtz free energy depend on volume, number of each I particle, and then the temperature, which temperature here is easier to control, or at least easier to measure. Next, we want to measure the volume here because the volume of internal system is too fluctuative, compressible, that compressibility itself makes us hard to measure the volume, and etc. So by this problem, we define H equals to this, which later we know this as enthalpy free energy. And if you take the differential form of H, we will get this, which by this differential form, we get that enthalpy depends on entropy, pressure, and the number of each particle I. Neglect any fluctuation of the volume. And the last case in this video, I don't want to measure the entropy and the volume in the same time because these two in microstate is too fluctuative, too uncontrolled, and sometimes unnecessary, and etc. So then we define G function as this equality, which we know that G here is Gibbs free energy, and by differential form, we will get the final result as this, which depend on the temperature, number of each I particle, and then the pressure, which these variable easier to control and measure. And the summary of those all three cases is the most famous function that used in engineering, especially in thermodynamics point of view. But is this three function just the only result of Legendre transform? Well, there is another combination that I will leave to the viewer to solve it. And that's how powerful of Legendre transform, especially in thermodynamics and maybe next time in analytical mechanics in physics. I hope you enjoyed this video. If you like this video, don't forget to share, hit the sub, and of course, if you have any questions, write down in the comment below. And that's it. See you later.